So I'm going to talk about the main project of my PhD, and that's a search for the electron's electric dipole moment. Dima already did a great introduction to why we do stuff like this, but before we get started, I'm going to give you a quick overview of the standard model. Okay, so here's my depiction of your average high energy theorist, and they are busy enjoying the success of the standard model. And the standard model, as we all know, is really one of the greatest achievements of modern physics. Almost every time we test it, the predictions agree with the results to really exquisite precision. It's quite beautiful. But unfortunately, when it is wrong, it's really wrong. So for example, the standard model does fail to explain the baryon asymmetry like Dima mentioned. That's just the imbalance between matter and antimatter in the universe. There's all sorts of other problems like dark matter, dark energy, and of course, quantum gravity. But for now, we're just going to focus on the small problem of the fact that we all exist. So the problem with the standard model is that it's a bit too symmetric. It needs some more symmetry violation. In particular, it needs CP violation to explain things as fundamental as this beautiful conference. So theorists, of course, have been busy creating new models to explain our existence. And those new models have the extra symmetry violation we need. Some of those new models predict that fundamental particles like electrons have more CP violation than standard model electrons. Okay, so that's how the standard model works. So like I mentioned, a lot of these new physics theories predict that electrons have more CP violation, and thanks to the CPT theorem, that means time reversal symmetry violation. So at the top, I have what's probably a fairly offensive cartoon depicting why an electron EDM will violate time reversal symmetry. You can just see that if you flip the arrow of time, the spin flips, but the EDM doesn't. So that violates time reversal symmetry. At the bottom, I have a cartoon indicating the current status of the field. So I've indicated most new physics theories in pink, and they predict electron EDMs right in the range that we can actually measure. So every measurement we do constrains these theories. The standard model prediction, which I put in brown, predicts an electron EDM orders of magnitude away from where we are. So that means that we have a background-free measurement, which is very nice. In blue, green, and yellow, I've indicated a timeline of the leading results in the field. And you can see that we've actually been moving along at a remarkable clip. We seem to, as a field, cut out about an order of magnitude every 5 years or so, which is really incredible. A high energy theorist actually once told me that neutron EDMs are responsible for killing more theories than any other experiment. And sometimes that's the only thing that keeps me going. But for real, EDMs are actually a very, very powerful probe of new physics. The current best result done by the ACME collaboration constrains new symmetry violating physics at the 30 tera electron volt level. And that exceeds the reach of the LHC. That's amazing. So hopefully I've convinced you that measuring EDMs is a worthwhile endeavor. So the next question is, how do you actually go about measuring something like this? So I want to start by having you just imagining a simple spin flip measurement. If you measure this in the presence of a magnetic field, you'll get some energy. Now I want to add in the effect of the EDM. So imagine that it points in the same direction as the spin. So the little ket represents both the electron EDM and the spin. If you add this in plus an electric field, you'll see that that pushes the levels together for this relative orientation. Now, if you flip the electric field, it will push, farther apart and together. So the point is, because you're measuring something really small, you want to do a differential measurement. You can take the difference between those two measurements. The magnetic term will cancel out to first order, and you'll have a measurement of the electron EDM. This is actually the general idea behind all electron EDM measurements that I'm aware of. So as far as we know, the electron's EDM is very, 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 very small. So we're obsessed with sensitivity. So for good sensitivity, there's 3 major things that you need to consider. First, the larger the electric field, the larger the splitting will be. Second, a larger count rate will allow you to determine the centers of the peaks with more precision. And finally, a long coherence time will give you narrower resonances. So our sensitivity, which I've indicated in the bottom there, scales like 1 over the electric field, the coherence time, and the square root of the counts. So for a measurement like this, it's really important for us to maximize all of these parameters. So to start with, we want the electron to experience a truly enormous electric field. This is the main reason why all of the leading electron EDM experiments are currently done in paramagnetic polar molecules. So the unpaired electron spin will experience a massively enhanced electric field inside of the polarized molecule. And the beauty is that this only requires modest laboratory fields to produce. So in our lab, we have a laboratory field of 50 volts per centimeter, and this gives us a field inside the molecule of 20 gigavolts per centimeter. So that's very beautiful, but of course, nothing is free. We all know how complicated molecules are compared to atoms, and I know I'm breaking the rules of this conference by not even giving you a simple atomic bit system. So for every electronic state, you have rotational states, vibrational states, and then if you add in things like hyperfine splitting and Zeeman sublevels, from the perspective of a spectroscopist, you actually have a really huge mess. So this can be both a blessing and a curse. It's a blessing because we're able to exploit certain molecular states to improve our measurement, but it's a curse because it actually makes the vast majority of molecules that are actually sensitive to the EDM almost impossible to trap and cool. So for this reason, until Eric conceived of our experiment, all molecular EDM experiments were done with a beam. So that means they had neutral molecules flying through the lab, being prepared and read out in a matter of milliseconds. So beam folks are stuck. They have a very short coherence time, so they chase after a large count rate, which obviously they've been incredibly successful with. But say you actually wanted to increase the coherence time, what you have to do is cool and trap the molecules. This is super difficult with neutrals, but there's tons of groups working on the technology to do it right now. And I expect in the next 5 or 10 years, we will see that happening. But Eric had a different idea, and that was to use molecular ions, which are obviously super easy to trap. The clever bit, and the reason why nobody else uses ions, is how you polarize them. So obviously, if you apply a static electric field to polarize a bunch of ions, you can't keep them trapped. So Eric's idea was to use a rotating field and to do our spectroscopy in the rotating frame. So with this scheme, we have coherence times 3 orders of magnitude larger than beam experiments, and this is not under the square root. So this is beautiful, and we're still the only, well, in my opinion, and we're still the only people in the world using rotating fields to polarize trapped ions. Now, since the electron EDM is effectively 0 at our sensitivity, but we always want to measure a frequency, we need to bias our measurement away from 0. So we need a magnetic field to measure a spin precession frequency. So at this point, you might be asking, how can we make a rotating magnetic field? Well, with our setup, the ions are driven in uniform circular motion by the electric field, and they make small circular orbits with about 0.5 millimeter radius. In the presence of a quadrupole magnetic field gradient, these circular orbits have the effect in the molecule frame of a static magnetic field that's either aligned or anti-aligned with the quantization axis. So the primary component of the spin precession frequency that we measure is actually due to this so-called rotating magnetic field. So taken together, these are the basic ingredients. There's one more really important thing that we need to do. So a key element of our experiment is blinding. So as you know, with delicate and sensitive measurements, it's really easy for experimentalists to want their result to match all of the previous results. And what can happen is that experimenters will accidentally or subconsciously bias their analysis or even their data collection to make this happen. So we collect our data blind. You don't do it like this. One great example of the motivation for blinding, one of my favorite examples is actually the speed of light. You can see that there's 2 chunks that kind of drastically deviate from the accepted value. And people conjecture that it was because of that exact effect, like someone did a measurement and then all the following measurements, until a very brave person came out and did the right thing, people were like biasing their result to match the previous results. So we do collect our data blind, and what that means is we actually just add a randomly generated number to all of our measurements, and we do all of our data collection and all of our analysis with that number added in. We don't unblind until we're ready to publish. So that's the general sense of our experiment. And now I'd like to go over a few details to give you a sense of the complexity. Theorists, feel free to check your emails. I think even professors won't like these next few slides. This one's between me and the graduate students, just so I can have you all feel sorry for me, because you're going to see how complicated this one is. So the first thing is making our ions. We ablate a piece of hafnium in the presence of sulfur hexafluoride, which through the magic of chemistry makes neutral hafnium fluoride. So we supersonically expand the neutrals until they're about 10 Kelvin and they fly into the trap. Once they're there, we hit them with 2 photons to ionize them just above the ionization potential, and they decay preferentially to the ground singlet sigma electronic state. So far, this has required 5 lasers, which I'm going to put in the sidebar here. I'll keep track of the lasers as I go, just so you guys feel really sorry for me. And just as a note, our ions don't get cooled anymore. They stay at about 10 Kelvin for the duration of the experiment. We don't need to worry about something like Doppler broadening, because we do Ramsey spectroscopy and we measure a precession frequency, not a laser frequency. So the next thing we do is we need to transfer our ions from the ground electronic state to the eEDM sensitive state. We do this incoherently with a laser that connects singlet state to a triplet state via triplet pi0 state. Someone might be like, wait a second, this violates selection rule. Actually, the intermediate state has a mixture of singlet and triplet state, so it's fine. Unfortunately, because this is incoherent transfer, it decays from upstairs into a multitude of vibrational states downstairs. This is a problem. The higher vibrational states will decay into our science state over the course of the experiment and contaminate it. So we clean it up with several more lasers. And this leaves population only in the triplet delta 1, V equals 0, J equals 1 state. So now, our molecules are spread out over the Zeeman sublevels, but we need to start with a pure spin state. So we pump the population into one of the stretch states with strobe sigma polarized light via triplet pi0 transition, which preferentially decays back to triplet delta 1. So finally, now we have a pure spin state. So there's one more detail, it's called omega doubling. Basically, the molecule has a molecule frame dipole moment, and in the presence of a magnetic field, states of good parity will mix into states of good orientation. So the orientation states are either aligned or anti-aligned with the electric field. We call these Stark doublets, or doublets for short. I'll probably use the word doublet by accident throughout the rest of this talk. So what happens in the 2 doublets is the magnetic field will shift the MF sublevels, and thanks to the orientation, due to the relative orientation of the spin and the internal electric field, you can see that in the upper doublet, the levels are pushed apart, and in the lower doublet, the levels are pushed together. So our measurement is the difference in precession frequency between these 2 doublets. Unfortunately, it's not so easy. The G factor is also different between the 2 doublets. So we need to be careful when we're subtracting essentially the frequencies between the 2 doublets to get the part that's only due to the eEDM. So back to the Ramsey spectroscopy, I've indicated population with like a little green blob. What we do is, in this example, I'm starting in the spin down state in each doublet. So I apply a pi/2 pulse to create a superposition in each doublet. And then we let the states evolve, which I've animated that way. And then we, after a varying amount of time, we project the state into one of the spin states by depleting one of the stretch states. So ultimately, our results will look like this. This is a measurement of the spin asymmetry as a function of free evolution time. Because of those different G factors and a little bit because of the electron eEDM, you see the upper and the lower doublets start in phase they go out of phase, and then they come back in phase. This is actually much more recent data. We usually just measure the early phase and the late time phase, and we try to average down mostly on the sides of the fringes where our sensitivity is maximal. So just back on my laser diagram for completion, I've added in a little orange arrow for depletion. And then our final step is dissociation. That's our readout. We count the relative populations via dissociation. And what we do is something a little bit clever. We actually use the orientation in the traps that we can simultaneously measure the population fold. Then we kick our ions to the detector, and the clever bit is that the ones who are facing one way, their hafniums go to one side of the detector, and the ones who are facing the other way, their hafniums go to the other side of the detector. So on our detector, what we see are two blobs corresponding to the same doublets, and we count the ions in either the left side of the screen or the right side of the screen and perform a differential measurement between the doublets. So running a very complicated measurement with 14 lasers is exhausting. That's another reason why I'm sitting right now. But we're doing okay. We're actually doing our data run right now. Our current status is 42 microhertz uncertainty. So we've tied with the leading results so far. And we're at about 130 hours of data. What you're looking at is just all of our individual measurements of the measured frequency difference. We have about 400 measurements. Each of those are about 20 minutes each. So this is already 130 hours of data. Also, just to note, in sort of a fractional uncertainty, our primary fringe frequency is between 100 and 200 hertz. Our uncertainty is 40 microhertz. So this puts us at about a part in a million. Not as amazing as clocks, but still pretty sweet. So our projected result with about 800 hours of data should put us about a factor of 2 past ACME. And one thing to appreciate here is that ACME does their experiment with neutral molecules, different species in a beam, while we use trapped ions and a different species. So our experiments are really complementary. We're competitors, but I really think that we're kind of on the same team because we have two totally different systems with two totally different sets of systematics. So when our measurements agree, it is a lot more comforting than if we had two very similar setups. And when you're measuring zero, you want to be sure. Again, getting 800 hours of data is totally exhausting, but I'm what, a third of the way there, let's say, approximately. Just kidding, it's a fourth. So looking forward, we obviously want to keep pushing this exclusion lower and lower until we find something non-zero. And ultimately, we might have to go all the way to the standard model prediction, which will be disappointing. But our current setup is going to run into serious difficulties really soon. We're very limited in the count rate because we use trapped ions. You can only trap so many, and you can only do one experiment at a time. You prepare them, send them in the trap, wait, read them out, do da-da-da, right? So we could increase our coherence time, but then our rep weight would go super low, and getting something like 800 hours of data would take years. So Eric is never one to be fooled. He has invented a brand new solution that he calls the bucket brigade. So the bucket brigade is a kind of hybrid beam trapped ion experiment. This is an artist's depiction, but essentially what we're doing is we're stacking ion traps on top of each other, and that allows us to run 100 trapped ion experiments in parallel. What's actually happening is it's a very long apparatus. There's a preparation chamber at one end, and then so you're like, no. And then 100 stacked ion traps, and then a readout chamber on the other end. So what you do is you make an ion cluster, prepare them, and then send them into the beam for the free evolution time. And then you make another one, prepare them, and send them into the beam. So you have a full beam of little ion clusters. And at the other end, you read them out. This is honestly a pretty brilliant idea, but again, no one's ever done it. And it's going to be quite, yes, a lot of, I'm seeing grad students all shaking their heads. Yeah. It's going to be a difficult experiment, but the team that's working on it has already made incredible progress. They've actually already built the first prototype of what they call the baby bucket. And what they're going to do is they're going to have a chamber and then the bucket, but not a readout chamber at the other end. So they're going to prepare and then do like a little back and forth and read it out. They also are using a new species where the science state is the ground state. So our coherence times can become really long. We're expecting coherence times on the order of 20 seconds. So it's another order of magnitude larger than where we're at now. So looking forward, this will put us somewhere around here, which is just on time for all the other neutral teams to figure out how to cool and trap their molecules and hopefully keep us all competitive. Now, before I run out of time, very quickly, as promised by Dima, I'll talk a little bit about time varying EDM. If I wasn't busy enough with 15 lasers or 14 lasers, I did a little dark matter exclusion using our old data. So Victor Flambaum came one day and told us that a cosmic dark matter field, such as axion-like particles or ALPS, will take a static EDM and transform it into an oscillating one through some coupling where it oscillates at the Compton frequency. So what we wanted to do was analyze our previous data set from 2017 as a function of real world time. So essentially the time at which it was actually acquired to see if we could see an oscillating signature. So with this previous data set, we were actually able to constrain the coupling strengths over 7 orders of magnitude in axion-like particle mass. So I'm not going to get into the details here because obviously I don't have time, but basically what you do is take a Fourier transform of your data, you get a super noisy piece of garbage like this, and what you want to do is figure out if any of these peaks actually correspond to a real dark matter signal or are just noise. I spent about a year reading what other people had done and reading a bunch of textbooks, and what we found out was that other groups had made quite a few mistakes in their analysis. So we developed a new Bayesian analysis, which hopefully accounted for the shortcomings from other research. And just to be polite, we did not have a competitive result at all. Our result is here in pink, which I felt was a nice balance because in our paper, we kind of told a few people they were wrong. We are the first laboratory constraint over 2 orders of magnitude, and we are the first paper that I know of to correctly account for important sources of attenuation, like the finite line width of the ALP field, or even the finite sample collection time. So there's a lot of precision measurement people in this crowd, and I think exclusions like this are going to become more and more common. And so I would encourage you to read our paper. I suffered so that you don't have to. So that's it. Thank you so much.
Thanks very much, Tanya, for this very nice talk on a really smart experiment. Questions?
So when you dissociate these molecules, can you just say what you do? So you go directly to a repulsive state, or is it pre-dissociating state?
Yeah, it's oh, I don't have the levels. So it's we initially, the first photon goes to a bound state, and the important aspect is that bound state inherits the angular momentum character of the state that we're dissociating from. And then we go to a dissociative state.
Because the dissociation might not be instantaneous, yes, depending on the mechanism.
So it's about, I think, 20 nanoseconds, which on the scale of how fast we're spinning is fine. We spin at about 350 kilohertz, if that's the time scales that you were worried about. Yeah.
Thank you. Thank you.
Thomas.
It seems to me that you're winning a lot on coherence time, as you explained, but you're also losing because you have only a few particles, right? So now I'm wondering wondering if you plug this into the sensitivity expression that you had, how does it actually compare to acne?
Oh, yeah. So we basically tie with them every time. And that's because they have like 6 orders of magnitude more molecules that they read out, but we have 3 orders of magnitude more coherence time, and they're under the square root where we're not. So it ties pretty much.
Thanks.
Yeah.
What is limiting your coherence time at the moment?
Rep rate, really, our like excited state lifetime is about 3 to 4 seconds. And we measure, we change our fringe frequency all the times, and we like to measure at the beat where they come back into phase with each other. That's where you get the perfect noise cancellation. So we measure out to about 1.5 seconds and sometimes out to 2.5 seconds. But that just, the longer you go, the lower your rep rate gets and the slower the data rolls in.
Any other question? Yes.
Okay, thanks very much for your very nice talk. It's amazing and beautiful. And it seems that you are ready for your PhD defense. Yeah.
Very ready.
Yeah. Okay, I have a question about this 10K. I mean, is there a specific reason to choose this 10K, and what is the impact of this fluctuation to this temperature fluctuation?
Oh, 10 Kelvin is just what we get when we supersonically expand the neutral beam. We would love for it to be colder, but that's just where we end up. So it's not that specific other than it's just an experimental constraint. Yeah.
Claudio?
Yeah, no, just to know how many molecules do you have in the trap at each time?
Oh, yeah. So we actually trap between 20 and 30,000 molecules. Our trap is huge. If anyone knows ion traps, they probably know something really small. You could put like a whole Starbucks coffee inside my ion trap. It's enormous. You could put your fist in it. Sometimes I want to. So we trap about 20,000, but because we have all these steps and our molecule is totally unwilling to be controlled, every step in state preparation has an efficiency less than 1. So what we actually read out on the side of a fringe is about 500 out of 20,000. It's devastating. Yeah, so this image here on the far right is an overlay of about 20 images just so that you could see the 2 blobs better. But what you would see would be just, 250 dots on one side and 250 dots on the other side.
Hi, I have a question about the blindfolding.
Mm-hmm.
So to which quantity exactly do you add the random number, and then how do you extract it in the end?
Oh yeah, so we basically take the difference frequency between 2 fringes in a slightly extra complicated way so that we can get rid of the magnetic term and are only left with the electric dipole moment term. And that's where we add our random number. And what we did was we, like 2-3 years ago, we generated the random number. It's stored as a text file in binary on our computer. So you can't just like click on it and read unless you can read binary. And that's what we add the random number to. And then essentially, every time we plot or every time we look at anything, that random number is added in. And all we have to do is comment out that line in the analysis in our final analysis. So it's fun when you unblind. It takes like 30 minutes because you have to reanalyze 800 hours of data. And the first time we did it, we all sat in a meeting room together and got pretty nervous that we were going to get non-zero. But luckily it was 0.
Thanks.
Okay. I don't see any. Maybe one very quick question at the end. You've been talking about a new experiment and a new species.
Mm-hmm.
Is this a secret, or what's this new species you're
Oh,
considering?
no, it's not a secret at all. It's thorium fluoride.
Okay, I see.
Yeah.
How does it compare to hafnium fluoride in units of field strength?
It's 1.5 times larger internal electric field.
And ground state.
Yeah, and the science state is the ground state. So we're expecting about 20-second coherence
Why
time.
didn't you start with this?
It's
Because
already,
you just found it.
yeah, so for time scales, I mean, there's a lot of precision measurement folks in the crowd, so you guys are used to this, but other grad students are like, what? like the thorium experiment started in 2013. And they had to do all the spectroscopy on the molecule because no one had ever worked with it before. And now they've just started building the apparatus. So maybe in 3-ish more years, they'll have like a measurement.
Okay.